Okay, so let me welcome Leszek for the second time to MOPA, and this is the second half of Ramsey's theorem for RCA0 star.
Right, thanks for the extending the invitation in both senses of the word extend. So I will continue my talk from August, and just to remind you over the overall picture, it's about, well, a reverse mathematics style analysis of Ramsey's theorem, both for pairs and for tuples of larger length. Over this weaker theory, RCA0 star, I'll recall what that is in just a moment. It's a weaker base theory than the normal one that they use in reverse mathematics. And it turns out that I would say the proportion between a computability theory and model theory of arithmetic changes to some extent if you're doing reverse mathematics over RCA0 star in favor of the model theory of arithmetic, which is already relevant if you're analyzing things like Ramsey's theorem in the more classical setting over this theory RCA0. But if you drop the sigma 1 induction, which is what you do to get this star theory, then actually model theoretic aspects of the picture start to matter even more. So a quick reminder of some basic ideas from last time. So I won't review the basic definitions. I assume that you saw them last time and you kind of remember them. The base theory we're studying is RCA0 star, and this is formalized in the language of second order arithmetic by taking delta 1 comprehension or delta 0 1 comprehension. We're allowing, the 0 means that we're allowing, the superscript 0 means in the notation I'm used to that we're allowing second order parameters, but other than that it's delta 0 1. So delta 1 without the 0 would mean like light phase without the parameters. So we're allowing, delta 0 1 comprehension, bounded induction, which means in fact delta 1 induction, therefore sigma 1 collection, because we have the comprehension. So bounded induction applied to a set that was obtained by delta 1 comprehension is essentially delta 1 induction. And finally, we have the axiom X. So we do have the exponential function to avoid making the theory overly weak. Yeah, this is the base theory. And last time I talked about Ramsey for triples and larger lengths. Today the focus will be on pairs. To recall briefly some things from last time, I'll ignore that. I had a slide at which I kind of I started somehow, I stumbled there a bit because there was some sort of corollary that seemed false to me during the previous talk, and that was false. If you ever looked at that, that was some sort of obviously false statement, but it didn't matter in applications. So just ignore that and don't worry. Let me recall some basic things that we proved last time. So here's, I would say, the foundation for all the later work. If you're working in a model of RCA0 star, which is not a model of the usual base theory for reverse maths, RCA0, which means it's not a model of sigma 0 1 induction. Then you have a proper cut that's sigma 1 definable. Let's call the cut I. And if you're given this cut I, it has a natural second order structure on it, inherited from the first order structure of the universe of your original model. Basically, the traces of the M finite sets, or the coded sets as you prefer, their traces on I. And it turns out, the proof isn't very difficult, but this was certainly a surprise once we first realized this, that the original model, whatever its second order universe was, satisfies Ramsey for a given tuple length exactly if the cut with the coded sets, a second order universe satisfies Ramsey. This doesn't depend on the second order universe of the original model, and this doesn't depend on the cut as long as it's sigma undefinable. So over RCA0 star, once induction fails, Ramsey is really governed by the structure of sigma undefinable cuts. And we used that to observe another interesting thing, used that plus some coding features of a lemma by Chong and Morad about what you can code in models of well, sigma 1 collection, basically, to show that if you have a model M satisfying Ramsey, and in this model you have a set that fails sigma 1 induction, then actually Ramsey is already satisfied. Well, this essentially follows from the equivalence I just gave you with Ramsey on cuts. Is already satisfied by the delta 1 definables in the set A that violates induction. So in particular, if you don't have sigma 1 induction, it can happen, unlike what happens in the real world, that you can have all computable colorings of pairs or even of triples or whatever length of tuple you want. It might be the case that all of them have computable homogeneous sets. So that's something really new. The usual proof due to Jokic that computable colorings don't, there is a computable coloring that doesn't have a delta 1, even in a delta 2 homogeneous set, that requires more induction. So this sort of thing happens, and we had some notation for it. This notation delta L, R, and T, and 2 means that Ramsey for n tuple holds in the delta L definables. So for every delta L definable 2 coloring of n tuples, whatever n is, there's going to be a delta L definable homogeneous set, where homogeneous, of course, means infinite homogeneous. And this stuff plus some other things that were specific to triples, I'll skip that. We used that to give a complete characterization of the first order consequences of Ramsey for triples or for longer tuples. Our emphasis here in this work was on understanding the first order consequences. In the traditional reverse mathematics settings, Ramsey for triples and beyond is well understood. Here it turned out to be easier to understand as well, although the first order consequences become a bit strange. In the traditional setting, they would simply be PA. Here they turn out to be this really strange theory that basically says that if you don't satisfy PA, then the last level of the usual hierarchy of fragments of PA that you satisfy is collection and not induction. And if that last level is, say, sigma 4 collection, then the universe of delta 4 definable satisfies Ramsey's theorem. So that's the theory you get, and it's kind of strange. It's an non-finitely axiomatizable fragment of PA that is in particular pi 3 conservative over B sigma 1 plus X. So it's a rather strange theory, but we got a precise characterization of that. And today I wanted to talk about pairs. Ramsey for pairs is not fully understood in the traditional setting where you have sigma 1 induction in the base theory. We now know that it's pi 3 conservative over B sigma 2 and therefore over I sigma 1, but that's a result of a relatively recent result of Patei and Yokoyama. And we know that Ramsey for pairs plus sigma 2 induction is fully conservative over sigma 2 induction. So Ramsey for pairs doesn't add anything to sigma 2 induction, which makes it weaker than the variance of Ramsey for longer tuples. But there are still open problems. And it turns out that in the case of Ramsey for pairs, there are also questions over RCA0 star that we can't answer about its strength. Some of that is simply due to the fact that we can't determine its exact strength over RCA0, but some questions turn out to be specific to RCA0 star, and I wanted to mention basically both kinds in this talk. So let's state something that's maybe it's maybe excessive hype to call it a theorem, but let's look at what the first order consequences are of Ramsey for pairs and two colorings. Of course, we showed that increasing the number of colors as long as it's fixed doesn't do anything. So let's look at the first order consequences of RCA0 star plus Ramsey for pairs, assuming various amounts of induction in the ground model in the purely first order universe. So let's see what Ramsey for pairs does over RCA0 star depending on how much light phase induction the ground model has. So firstly, these first order consequences, they add nothing to sigma 2 induction, because even if you had RCA0 in the base theory, they would add nothing. That's this result I mentioned a few moments ago due to Cholak, Jokush, and Slayman. The paper is 2001, I believe. Yeah, Peter, it's 2001, right? Doesn't really matter, but yeah, I mean, we've got one of the.
I don't remember. I'm sorry.
You don't remember? No problem.
I mean, I can look it up.
Yeah, I guess there is no need to, but this was one of the major papers on the way to understanding the strength of Ramsey's theorem to the extent that we now understand it, which is not fully, but this was one of the few most important papers in this area.
Leszek, quick question. When you say are contained in I sigma 2, what does it really mean?
Yes, so that means that if you have a statement psi and RCA0 star plus RT22 proves it, then I sigma 2 proves it. And let me give you a model theoretic argument. Let's say that you have a model of I sigma 2, then satisfying something, some first order sentence, however weird it is, but it's satisfied in the model of I sigma 2. Therefore, there is a structure, a second order structure over that model satisfying RCA0, simply take the delta 1 definables. And then, assuming this is a countable model, Cholak, Jokush, and Slayman tells you that you can extend the second order universe, keeping the first order universe unchanged. That's what they call an omega extension, to satisfy Ramsey. So anything that follows from Ramsey will follow from I sigma 2. Anything that's consistent with I sigma 2 will be consistent with Ramsey. Even if you strengthen the base theory, even if you drop the star, okay? So the other extreme is if the first order model doesn't even satisfy sigma 1 induction. And in that case, Ramsey for pairs is actually axiomatized by computable Ramsey for pairs. So computable two colorings of pairs have computable homogeneous sets. And we're not going to prove this because I basically sketched the proof of the analog of this part for Ramsey for triples, and the proof doesn't change at all. So this is something that is basically covered by the techniques from, well, I was going to say last week, but last week means something like 6 weeks ago, or 6 plus epsilon, whenever it was, well, I guess 6, right? It's always Wednesday, so it was probably 6 weeks ago. So then if we're in a model of B sigma 2 and possibly not I sigma 2, then what does Ramsey tell us? Here, there's not much that I can say. So if something is provable from Ramsey for pairs in RCA0 star and B sigma 2, then it's going to be provable from Ramsey for pairs in RCA0, simply because RCA0 implies B sigma 2. And it's also going to follow from this strange axiom delta 2 Ramsey. So any delta 2 coloring of pairs has a delta 2 homogeneous set. And actually, both of these things are consistent. So both of these things can happen in a model of Ramsey plus RCA0 star plus sigma 2 collection. So there's not that much more that we can say about this. And an interesting case is we wondered about is whether it is conceivable that Ramsey for pairs over RCA0 star actually adds nothing to I sigma 1. So whether it's conceivable that everything that's consistent with I sigma 1 is consistent with Ramsey for pairs in RCA0 star. This would not be true if we had RCA0 in the base theory, precisely because RT22 plus RCA0 plus sigma 2 collection. But it's not clear whether we have that over RCA0 star. So this was something that we legitimately wondered about for a while. So yeah, as mentioned, if we had sigma 0,1 induction, then that would immediately give us sigma 0 to collection. I recall this convention that the superscript 0 means we're allowing parameters. So it's boldface sigma 1 and boldface sigma 2. But the proof of this, it's not a difficult proof at all. It uses sigma 1 induction relative to a second order parameter that you get from Ramsey. So it uses sigma 1 induction relative to a homogeneous set. This set doesn't have to be, well, in the light phase model, it doesn't have to be a computable set. Typically won't be, in fact. So, for instance, it's totally unclear whether Ramsey for pairs over RCA0 star, sorry, over the weaker base theory proves if I sigma 1, then B sigma 2. Ramsey for triples does that, but Ramsey for pairs, we don't know. So yeah, the question is there. Does Ramsey for pairs prove anything that goes beyond I sigma 1? And the answer will turn out to be yes. And in fact, this won't be something that's very specific to Ramsey. We're just going to use a particular feature that Ramsey shares with many weaker combinatorial principles. Namely, if you take RCA0 star, Ramsey for pairs, and you add light phase I sigma 1, then this theory implies every arithmetical sentence which is provable both from light phase B sigma 2 and from the negation of sigma 1 induction, possibly relative to some parameter. Okay, so if you've got a sentence that has to hold either if you have sigma 2 induction or if you sigma 2 collection, sorry, light phase, that's fine, or if you have failure of sigma 1 induction, not necessarily in the light phase model or possibly relative to a set, then that sentence holds. Then such a sentence will follow from Ramsey for pairs over RCA0 star plus I sigma 1. And this theorem is supposed to be obvious. Does it look obvious based on what's above it on the slide? Here are the 5 minutes for your reaction.
Not really to me, but.
Not really. So let's see. It's a pretty late hour here in Warsaw, so let me see if I can make sense of it. But yeah, I think it should be obvious. So, okay, so let's live in the model of RCA0 star plus Ramsey, and we've got light phase sigma 1 induction. Actually, the sigma 1 induction really doesn't matter. I think I would cross it out. It's actually not needed here, but we'll prove something that's not provable in sigma 1 induction. So actually, you can erase the sigma 1 induction from the light phase thing from the theory of Ramsey. So look at this model and ask yourself, does the second order universe satisfy RCA0 or not? So in other words, is sigma 1 induction also relative to set parameters? Is that still valid or not? If it's valid, then we're working in a model of RCA0. So we have in particular sigma 2 collection. So we have our sentence C. If it doesn't, then we're in a model of not I sigma 0, 1. So we also have C by the second half of the case assumption. Oh yeah, by the second case of the case distinction. Okay, so yeah, so this really is pretty obvious. This is designed to be like the obvious thing. The less obvious issue is whether there are any such sentences or whether this ever happens. Are there any such C? And the answer turns out to be yes. Okay, so are there any steady statements like that? Yes, there are. And here's an example. So this is a statement. It's been studied in at least 2 variants. I took the variant defined by Richard Kay, which is called card. There is a slightly, now which is it, weaker or stronger? A slightly weaker variant, I guess. There's a slightly weaker, there's a slightly weaker variant denoted using just the letter C instead of card. Both are called the cardinality scheme, I guess. The other variant was studied by Seidel and Slayman. They differ if you're depending on whether you're only interested in functions or in multifunctions. But basically, the stronger variant that I'll use. The sigma 2 should be sigma L. This is supposed to be, there's a mismatch of indices. So this says the cardinality scheme for sigma L sentences or formulas says that there's no sigma L definable injection. We're also disallowing injective multifunctions. That's the stronger version. That's the Richard Kay version. That has as its domain the entire first order universe, and that has bounded range. So there is no extreme violation of the sigma L pigeonhole principle, right? There's no map from the universe onto A, where A is some number, or into A. Sorry, there is no map into A, and we're even disallowing multifunctions. Okay. So this principle, the sigma L cardinality scheme, is always provable from sigma L collection, in particular the sigma 2 cardinality scheme. This is a pi4 statement if you're interested in counting the quantifiers. This is provable, sigma L cardinality scheme is provable from sigma L collection. In particular, sigma 2 cardinality is provable from sigma 2 collection. Why is that? Because sigma 2 collection, and this will generalize to higher L as well, is simply the sigma 2 pigeonhole principle in the usual sense. So B sigma 2 says exactly there is no X and no multifunction from, and you can rule out injective multifunctions as well, from B sigma 2. There's no multifunction. There's no multifunction that would be sigma 2 definable. That would be an injection from X plus 1 into X. So the cardinality scheme rules out something that's much weaker. So sigma 2 collection proves it. On the other hand, sigma 1 induction does not prove the sigma 2 cardinality scheme. Why is that? Well, because the traditional model of sigma 1 induction and not sigma 2 collection, namely the pointwise sigma 2 definable model, that does not satisfy the sigma 2 cardinality scheme. There is an easily definable injective, possibly multi-valued map from the entire universe into something very small, essentially into omega, simply into the standard cut, namely take a number and map it to its definition. Okay, so this is something that lies between I sigma 1 and B sigma 2. And the interesting thing is that each of these cardinality schemes, not just for sigma 2, but for higher or levels of the arithmetic hierarchy as well, is actually provable from the negation of sigma 0 1 induction. Okay, so this is the interesting thing. So since it follows from sigma 2 collection and from negated sigma 1 induction relative to parameters, it's going to follow from Ramsey and RCA0 star. So this is our example that's provable from Ramsey even over RCA0 star, but it's not provable from sigma 1 collection. So the interesting thing that we need to do here is prove this theorem. So yeah, let's try to do that. We have 2 proofs. One is just take somebody else's proof and say that it works. The other is simpler and a bit more direct, although it's a bit strange as well. So here's the first proof. There is a paper by Kay where he shows that if you take any model of sigma 1 collection and totality of the exponential function and not sigma 1 induction, so the purely light phase model, no secondary structure so far, then that thing is elementarily equivalent to an aleph omega like model. So a model that has cardinality aleph omega, but each bounded segment has smaller cardinality. And we studied this paper with my student Kasia, and there is nothing there in our opinion that doesn't relativize. So if you've got a model with an extra predicate, which you can think of as a set coming from a second order universe that satisfies sigma 1 collection but not sigma 1 induction relative to that parameter, then it's also elementarily equivalent to an omega-like model. But obviously, sorry, aleph omega-like model, but obviously any aleph omega-like model satisfies the cardinality scheme. There is no injective map whatsoever from aleph omega onto a bounded segment of, or into a bounded segment of that model, because a bounded segment has smaller cardinality. So there is no, in particular, there's no definable violation of this cardinality scheme. In other words, that's your proof, right? B sigma 1 plus the exponential function, B sigma 1 relative to a set plus not I sigma 1 relative to some set implies the cardinality scheme because the model you're living in will be elementarily equivalent to a kappa-like model for kappa as singular cardinal. So that's the first proof. The second proof is I believe simpler, although it's still strange, and some of the ideas, I would say some of the combinatorics of that proof is actually the mechanism that's involved in the machinery pushing the K proof forward as well. So it's actually not completely different from that one, but we just took the ingredients that were needed. So let's take a model of RCA0 star plus not sigma 1 induction relative to possibly some parameter. And let's look at, let's consider if it could violate the cardinality scheme. And let's look at the automorphisms of this model. So mind you, I think we're doing really strange things. I mean, I'm used to assuming that if you prove a statement from a theory, you actually prove a statement in the theory. Here we're doing really strange things about models. I'm not that used to this. So if you've got a model that violates the cardinality scheme by means of a definable map, so you have some definable injective multifunction from the entire model into a bounded segment from 0 up to A, say, and this is definable with parameter C, then if you have any automorphism whatsoever of this model that fixes this parameter C that we use to define the injection and fixes the range of the injection pointwise, so it doesn't move anything below this upper bound on the range of the injection A, then that automorphism has to be the identity. There is no other way. I mean, we fix too many things, and therefore the automorphism cannot move anything at all. Okay. On the other hand, models of collection, and there is a negation missing here. This is my favorite kind of typo, a missing negation. It should say not I sigma 1 of A. So if you got a model with a set on it, a predicate on it, A, and this model satisfies collection relative to A, but doesn't satisfy sigma 1 induction relative to A, then that model has lots of automorphisms. This is known from papers of Roman and of K, and essentially it has its roots in earlier papers of Smolinsky from the 80s. I don't know how far back this line of research goes, but certainly there's much related stuff already in Smolinsky. Then such models have lots of automorphisms. In particular, if we've got an element B in this model that's above all the standard iterations of the exponential function on A, and we can ensure having such a B by trivial compactness argument, then because it satisfies collection but not induction, there is going to be an automorphism that fixes everything up to A. It then means that it fixes everything up to 2 to the A and up to 2 to the 2 to the A and so on, and fixes our favorite parameter C, but moves something, in particular it moves something below this guy, as pictured here. The moved object is marked in red. Okay, so models that fail the cardinality scheme have few automorphisms. Models that don't satisfy sigma 1 induction, but do satisfy sigma 1 collection because they're models of RC0 star, they have lots of automorphisms. So one can't be the other. Okay, that's the end of the proof. And therefore, Ramsey for pairs plus RC0 star proves something that I sigma 1 does not prove, namely the sigma 2 cardinality scheme. So here's a challenge. Here's a challenge for anybody, basically. Is there a way of coming up with a proof of the sigma 2 cardinality scheme, or maybe better yet, the sigma 22 or whatever subscript you want, cardinality scheme, from RC0 star and negated sigma 1 induction in some sort of more direct fashion? You actually take a statement and you prove it. I can imagine that one could work in this theory. We could give them a star, WK0 star. Some model theory can be done there, and maybe you can work in this theory WK0 star, define some model, and somehow try to reconstruct this argument. So that I can imagine can be done, but it's not clear to me how easy it is. I mean, generally model theory WK0 star is not that easy. Typically you have to work with various cut-free consistent theories because you don't have the cut elimination theorem. So it's not that clear. But is there any sort of proof that you just take and put it in half a page and that's it? I have no idea. So I think this is a nice challenge. Please think about it. Okay, so this is, I guess, more or less half of what I wanted to say. I'll just make a small digression on a different topic. There was a problem by Tausner. He had this paper on maximum conservative theories or something like that, where he proved that the following problem is pi2 complete in the computational sense. Take a pi12 sentence, say C, and is it pi11 conservative over RC0, the usual RC0, no star here. And he proved that this is pi2 complete, and he also proved that if you add sigma 0 and induction to both sides, both to C and to the weaker theory without the C, then this problem also remains pi2 complete. And he was asking what happens if you work over sigma n collection. So in particular, is it pi2 complete to determine whether a given pi12 sentence is pi11 conservative over RC0 plus B sigma 02? And we can now prove that the answer is positive using these properties of the cardinality scheme or related statements. It's not a very difficult proof. The problem in general, I mean, Tausner's problem is incredibly interesting, and we're going to write I guess a separate paper about it. But the really interesting stuff about it is the partial exceptions to a positive answer. The positive answer is not so shocking once you figure it out, although the proof is kind of weird. We're using this, probability of a statement that goes via automorphisms of models. So that's something I liked. This problem, I'm mentioning this because I've certainly talked to at least Roman about this problem and a number of people that could have been in the audience. So there it is. Okay, so I would like to partly switch topic now, because another thing we were wondering about, and in fact, this was the original motivation for looking at Ramsey over RC0 star, was that we wanted to know so some open problems over RC0 of Ramsey over RC0 star. So one thing that we don't know is whether it's conservative over B sigma 2, but I think this doesn't get solved until we fully understand the status of Ramsey for pairs in standard reverse mathematics over RCA0. So this one, to me, it looks kind of difficult. Never mind the second problem. I don't think it's that interesting, frankly. The third one, that one I do find interesting. There should be a star here. There's another typo in an unfortunate place. So in problem 3, it should say whether RCA0 star plus Ramsey proves sigma 1 induction implies sigma 2 collection, where you don't have the set parameters in the schemes. So this is purely light face. And we have no good reasons to think that it does. But frankly, it's kind of hard, apparently, to construct a model that would witness that it doesn't. So if you have a model that that you cannot extend to a structure satisfying Ramsey, then now am I making sense at this hour? What would it mean that it doesn't? Right. So that would mean that you have a model of RCA0 star plus Ramsey that satisfies I sigma 1 but doesn't satisfy B sigma 2. So if your model satisfied sigma 1 induction relative to all set parameters, then it would satisfy sigma 2 collection. So that means there must be a set in your second order universe, let's call it A, relative to which you don't have sigma 1 induction. And since we have RCA0 star in the base theory, you do have sigma 1 collection relative to that set A. And that puts quite a few constraints on this model. In particular, if you violated sigma 1 induction relative to the set in the most traditional way, namely by making omega the standard cut sigma 1 definable, then because of the connection between Ramsey in the entire model and Ramsey on cuts, that gives you constraints on the standard system of the model. So the standard system of the model cannot be a model of Ramsey for triples, for instance. So the standard cut cannot be a strong cut in the model. So it's not going to be that easy to answer question 3 in the negative, although we certainly don't have any good reasons to expect the answer is positive. Okay, so let me switch topic for the remainder of this talk. What we really wanted to know at the beginning was, well, this was a reason to study Ramsey over RCA0 star at the outset, before we realized that it's kind of interesting in its own right, was to see whether it could say anything about this traditional problem, or this open problem in traditional reverse mathematics. A major remaining open problem is to decide whether Ramsey for pairs over RCA0 is fully conservative over B sigma 2. So whether its arithmetical consequences are exactly B sigma 2. We don't know that. We know that they're pi 3 conservative over I sigma 1, as I mentioned, and they don't prove anything that's not provable in I sigma 2. So they lie somewhere in that realm, but they could coincide with B sigma 2, and we don't know that. So we were interested in getting some sort of insight into that. And well, this study that I've been discussing gives rise to potential sentences that could prove or witness a negative answer. So you start coming up with sentences that are not provable from B sigma 2, but could be possibly provable from Ramsey, now with sigma 0 induction in the base theory. Okay, so I just wanted to discuss an example and well, dismiss that example, but somehow my reasons for dismissing it will not be very general, so they might turn out to be very specific to this example. So consider the following sentence: if I sigma 2 fails, then you have delta 2 Ramsey for pairs, meaning each delta 2 coloring of pairs has a delta 2 homogeneous set. This is a statement that's provable over RCA0 star from Ramsey for triples. And RCA0 star plus Ramsey for pairs proves a similar looking statement, namely, if sigma 1 induction fails, then you have delta 1 Ramsey for pairs. Okay, so this looks kind of like it might conceivably be provable from Ramsey, at least over RCA0. If we strengthen the base theory, maybe it will be provable. It's not provable in B sigma 2. So if we can prove the statement in RCA0 plus Ramsey, then that's a separation of its arithmetical consequences from B sigma 2. So, well, the answer is that this, yeah, so here's the question. The answer is no. But there's, the proof, as you will see, is kind of curious. It's the only proof we really have. I mean, anything that we could come up with would be an obfuscated modification of this. We don't have like a genuinely morally different proof. And it's not only going to be curious, but it's going to be a bit specific to having Ramsey in this delta 2 world. If we weaken Ramsey to something, if we say that something weaker is satisfied by the delta 2 world, then the proof will no longer work, as you will see. So I think this is worth describing. So let's prove that Ramsey does not prove that if sigma 2 induction fails, then delta 2 Ramsey holds. Okay. You've been awfully quiet, so today, much quieter than in August. So I hope I didn't lose you in some basic definition or something. If there's anything,
I'm listening. I'm here listening. Just
okay, great.
Just so, you know, I hate the empty space, so I'm just trying. What I'm struck with is basically there's really so much between these theories, right? There's, you know, the gaps between them are very large, and that you could always put something in there in some sense. I mean, I'm you know.
By these theories, I guess you mean the usual fragments of first order arithmetic, or
yeah, well, with Ramsey, right? I mean,
yeah.
Various combinations of everything, right? They're almost independent. I mean, either they prove each other obviously, or they're really very different from each other, right?
Yeah, the interesting thing is what happens to me. The interesting thing is really what happens on the first order level, and the fact that we're discovering all these strange first order theories is quite fascinating to me.
Right, I agree. I mean, it's, you know, at the second order level, there's tons of separation.
There is this,
right?
Yeah, reverse mathematics zoo, right? You have all these techniques. They're mostly computably theoretic, and you have all these non-implications, but many of these theories have the same first order part.
Right, right, but it happens here too, but differently. But, you know, not, you know.
But differently, and yeah, and really exotic first order creatures are starting to crop up. So yeah, let me try to finish with this argument that we have, that Ramsey for pairs over RCA0, so usual reverse mathematics, doesn't prove the strange statement. If sigma 2 induction fails, then delta 2 Ramsey holds, or Ramsey holds restricted to the delta 2 sets. The proof is a proof speedup argument. So it actually uses results on proof lengths. So here's the argument. If you have B sigma 2, and if you have this statement that we're discussing, not I sigma 2 implies delta 2 Ramsey, then that implies that the following definable cut is closed under the exponential function. The cut of those x such that every infinite meaning unbounded, delta 2 definable set has at least x elements. So if sigma 2 induction fails, then you might have an infinite, in the sense of unbounded, delta 2 definable set that doesn't have x elements for a large enough non-standard number x. That's exactly what failure of sigma 2 induction means. And nevertheless, if you have this particular statement, then you get closure of the set of x's such that every delta 2, infinite delta 2 set has x elements. You get closure of that under the exponential function, essentially because finite Ramsey numbers are exponential. That's the underlying reason for this, in fact. So this reduces to finite combinatorics. Now, this cut, the cut of those x such that every infinite delta 2 set has at least x elements, is essentially, give or take 1 or 2 exponentials, a measure of how consistent I sigma 1 is in the cut-free sense of consistency, with additionally, any sigma 4 true sentence, true in the sense of true definition, added to that. So basically this says that if I sigma 1 plus some other stuff, never mind, that is cut-free consistent with respect to proofs of x with x symbols, then it's also cut-free consistent relative to proofs with 2 to the x symbols in them. Then you do traditional shortening of cuts argument known from Solovey's unpublished work and Pudlak's papers and so on. And this turns out to mean that you can prove in this theory, using this extra sentence that we started with, by a polynomial in n size proof, the cut-free consistency of, in particular, I sigma 1, up to proofs of the size super exponential, this is the iterated exponential function, of the super exponential of n. So these are enormous proofs. And now applying the usual bounds on cut elimination, this means that the statement we're considering, this not sigma 2 induction implies delta 2 Ramsey, it implies by a small proof, by a poly in n size proof, the consistency of I sigma 1 up to proofs of size super exponential in n. This means, by the so-called finite Gödel theorem or finitistic Gödel theorem, that the statement has significant proof speed up over I sigma 1 with respect to proofs of consistency statements, because, let me back up a slide, because the statement at the bottom here, consistency of I sigma 1 up to proofs of super exponential in n many symbols, to prove that in I sigma 1 you do need super exponential in many symbols. So this is what this finite Gödel theorem says, proved originally independently by Harvey Friedman and by Pavel Pudlak. So because our strange sentence leads to a quick proof of this particular finite consistency statement, it has speed up over I sigma 1. But we proved in a paper with Keita and Lawrence, that's on the archive, it's been on the archive for a while, I guess we'll submit it within a few days, that RCA0 plus Ramsey doesn't have proof speed up over I sigma 1, not even for pi3 statements, so in particular, not for consistency statements. So RCA0 plus Ramsey doesn't prove our statement. It doesn't prove that if sigma 2 induction fails, then Ramsey holds in the delta 2 definements. Okay? So this, again, is a proof that was unexpected, at least to me, once when we started thinking about this. And then it turns out that this is the only way we know how to prove this. And another thing that I wanted to say about this, so the proof is not only strange, but it also relies on the fact that finite Ramsey numbers are exponential. So if you replace delta 2 Ramsey by delta 2 something, where the something is some sort of restricted version of Ramsey, restricted to colorings for which finite Ramsey numbers are no longer exponential, then the proof no longer works. So, for instance, an example of statement that would also give non-conservativity over p sigma 2, but we don't know how to determine whether it's provable from Ramsey or not, is the following. If sigma 2 induction fails, then you could call it the delta 2 chain anti-chain principle. Then every delta 2 definable partial ordering has a delta 2 definable infinite chain or infinite anti-chain. This is possibly provable from Ramsey. I kind of doubt it, but our proof of unprovability doesn't work for this one. This thing does not have proof speed up as far as I can tell for over I sigma 1. Another statement is that could be provable from Ramsey. It could also be provable from B sigma 2. In this case, we don't know. Is if I sigma 2 fails, then maybe each computable delta 2 coloring of, well, n tuples should be pairs, sorry for this, it has a delta 2 homogeneous set. So you allow the solutions to be delta 2 definable, but you restrict the instances of Ramsey to be delta 1 definable. And possibly this can be proved from Ramsey. Our argument, again, no longer works for unprovability of this. So there's a whole ton of statements that kind of naturally arise once you start studying these questions that could be provable from Ramsey and could separate Ramsey from B sigma 2. For a few of them, we can show that they actually don't separate, that they're not provable from Ramsey, but the techniques we use to do that are kind of strange, and moreover, they're very specific to those statements. If you weaken them just a little bit, they no longer work, so the situation remains intriguing. Okay, I guess this time I did manage to finish in time. So the last slide, I just wanted to list our references. Sorry, I'm only mentioning there are of course quite a few great papers that we're relying on, but I'm just mentioning the papers that we produced recently. There is this one by myself and Keita, where you have some bounds on Ramsey numbers in terms of alpha largeness, which is in turn used in this paper that I mentioned with Keita and Lawrence, that doesn't prove, where we show that Ramsey doesn't have proof speed up over I sigma 1. And we're basically done with the paper I've been describing today and last time. So the strength, or the first order strength of Ramsey's theorem over RCA0 star. Lawrence has told me that he has not contributed to this one, and he's very insistent that he has not contributed to this one. So it is possible that he will not be a co-author of this paper, but he's definitely a co-author of the larger project. And this paper is basically done. So if you're interested in seeing it before it's up on the archive, you can email me, and I guess I'll be able to send it out in a couple of days, basically. That's it. Thanks for your time. And yeah, that's all I have to say for today.
Okay, thank you. Thank you, Leszek. Time for questions.
Yes. In terms of the broader picture in reverse mathematics, the story we're usually told is there are these 5 or more benchmark theorems, clean classification, which seems to break down here. You get more, looks like a fractal sort of boundary. Does that happen at the other boundaries also, or is the boundary different from the other basic boundaries in reverse math?
I'm not sure I understood the second half of the question. So certainly this picture that you have 5 benchmarks, the so-called big 5, has been shattered in some areas. I guess it's still relevant. We have an actual expert in reverse mathematics in the audience, but in combinatorics, or in particular in Ramsey theory, it's like clearly false, because there are incredibly many incomparable theories, and minor variants of statements turn out to be inequivalent. There is still most of the theories that have been studied for which we understand the first order consequences, for which we have a full characterization of the first order consequences. The first order consequences turn out to be one of a couple of theories, well, maybe not a couple, but a small number of theories that we're used to from first order arithmetic. So it's not as totally strange in that respect. If we look in the base theory, then I guess more things become equivalent. So the picture is even wilder. And there also the first order consequences start to diverge as well, even in cases where they didn't diverge. over the stronger base theory. Although there is some sort of pattern, there's a method to this madness. There's some sort of pattern. It's not that you can't say anything. There are some interesting results. This is a matter for another paper and for another talk, I guess. But it's not that there's nothing interesting that you can say in general about reverse mathematics over RCA0 star. So there is a zoo. It's even wilder than over RCA0, but there is some interesting structure to the zoo, and I hope to speak on that another day as well.
Thank you.
So can I ask, what are the, if you just work over RCA0, the theories are just, I mean, they do get what's unknown about some of these things, right? But,
yeah, it's unknown. So for the ones that we know, I don't really know an exception from the that would not be I sigma 1, B sigma 2, I sigma 2, or PA, I guess. I mean, there will be maybe really strange examples, but
sure.
But I think the first order consequences tend to be typically that. And of course, we have lots of cases where we don't know, right? One is Ramsey. Another is these theories with well, for instance, this rainbow Ramsey theorem, right, where it proves the cardinality scheme, but it's not clear how strong exactly it is. It's possibly known. Is it known that it doesn't prove B sigma 2? That might be an example where it's known that it doesn't prove B sigma 2. There's this recent paper of Belanger and co-authors where they take delta 2 weak Koenig's lemma, and they show that its first order theory is a sort of weak sigma 2 pigeonhole principle, and they managed to show that it's strictly in between I sigma 1 and B sigma 2. So there are a few examples, but not that many, and you do need somewhat exotic second order statements, or at least not the most well-known ones, to get first order fragments that are known not to be any of the best known ones, that are provably something kind of strange. Am I answering your question?
Yeah, that's I'll have to look for that paper. So once I'm less overwhelmed with the semester. So
right, by that paper you mean for this delta 2 weak Koenig's lemma?
Yeah.
Yeah, it's a very nice paper. I have not read the second order parts, I have to say, the more typical reverse mathematics part, but I've read the study of the first order scheme, and it's very nice model theory of arithmetic. So I recommend it particularly to this audience, in fact. Yeah.
Okay, thank you. I'm happy.
Thanks.
Well,
Thanks.
you'll speak in our seminar, the Midwest seminar, in like 2 weeks.
Yes, I'll speak there. My tentative idea for that talk is slightly different. So
it's a different audience.
A larger number of statements over RCA0 star, also these ADSs and CACs and that kind of thing, and prove some reverse mathematics implications and non-implications. So not focus so much on the first order theories, but on a somewhat more reverse mathematics like picture.
Yeah, I mean, I don't think that audience really knows the difference between RCA0 and RCA0 star. So
yeah, that is my worry. But so of course I'll define it, but there's only so much computability that I could squeeze into a talk of mine, just because I don't have much computability. So
that's okay.
Don't expect too much from me in that respect. But there is some computability theory there. There is computability theory without sigma 1 induction. People have studied this.
Yes.
Chong and Moore, for instance. And well, some of that arises there.
Okay, we'll look forward to the talk. You guys, everybody else is welcome too to join us. So
yeah, that's October the 13th, I believe.
I'm looking. Yes. At 4.
Right, so it will be even later in Warsaw. I do apologize in advance that I fall asleep during that talk, but I'll try not to.
I muted myself, so no more questions. I don't hear any, so thank you very much again, Leszek, and see you
Thanks a lot
in 2 weeks then.